Today, our lesson is going to be on ellipses, and specifically how to write the equation of an ellipse. Now, the first thing is we need to make sure we understand what an ellipse is. An ellipse is an oval, but it's defined to be all points that are the distance from the point to two foci. So A is considered a foci, and B is considered a foci or a focus. The distance from A to a point on the ellipse plus the distance from the other foci to the point on the ellipse is always a constant. If you'll notice, now it's 5 plus 5, or it's 10. If I come out here, 2.68 plus 7.32 is also 10. All the way out here, we have 9. It's hard to see the 1, but plus 1 is also 10. So no matter where I'm at on the ellipse, the distance of these two line segments added together, the distance from the point to both foci added together, is always a constant. This one happens to be 10. This ellipse happens to also be centered at the origin. We're going to talk about centering the origin and making where the foci are. So let's talk a little bit more specifically about some parts of the ellipse. Okay, the ellipse has a center. It has two foci. It has two vertices, or vertex, two co-vertex. Okay, so let's stop there for just a minute and talk about those few things. Obviously, an ellipse, similar to a circle, has a center. It's not equal radius, obviously, because it's not a circle, but it does have a center. It has an elongated length. Now, the length from A to B is called the major axis. The major axis is the longest distance possible from one end to the other. The minor axis is the shortest distance from the co-vertices, one co-vertice to the next. Now, one thing I want to emphasize is that the major and minor axis the major doesn't have to be horizontal. I could actually rotate this, and then I would have to adjust I'm going to have to make this a little smaller, adjust the co-vertices now to be on the sides, and the vertex, the main vertex, would be above and below. So you can elongate it up and down. You can elongate it left and right. In fact, you could even do it slanted. That's a lot more difficult. We won't talk about slanted ellipses. We're just going to talk about the major axis either being vertical or being horizontal. So now I have my major axis as a vertical axis, my minor axis as the horizontal axis. Okay, again, the two foci are along the major axis a certain distance. And let's talk about those distances. We label them. The distance from the center to a vertex, so from the center out to a vertex, not a co-vertex, but a vertex, is designated as A. So the distance from here to here would be considered A. The distance from a co-vertex to the center is considered to be B. So from the center to a co-vertex is B. So now let's think about that, how it relates to a major axis. In other words, a major axis is twice A, or half the major axis would be A. The minor axis is twice B, or the value of length of B would be half the minor axis. The length C is the distance from the center to a foci. So from the center to a foci is the distance C. Now, one thing I want to emphasize is that we can use Pythagorean's theorem to relate A, B, and C, but I want to specify and to make sure you understand that do not confuse it with the way we normally write Pythagorean's theorem, because the distance from a co-vertex to the foci is the same as the distance from the center to the vertex. So in other words, remember, the center to the vertex is A. The center to a focus is C. C is shorter than A. And A is also the distance from a co-vertex to a foci. So A, in other words, is the hypotenuse of this right triangle. A is my longer side. So in reality, it would be B squared plus C squared equals A squared, but they write it in terms of an ellipse as A squared minus B squared equals C squared. Because remember, this length here is A, this length here is B, and this length here is c. So a squared minus b squared equals c squared. So don't confuse it with the way the Pythagorean theorem is written originally with a plus in between the a squared and the b squared. In terms of ellipses, it's a minus because a is actually the hypotenuse. Now let's talk a little bit about how we actually write the equation. The equation is written in this form where we have our center as a horizontal and vertical shift. So similar to circles, we have squareds like we had on our circles in the last lesson, but we have an x minus our horizontal shift. So for this specific one, h would be 4. X minus 4 squared, because my center of my ellipse is 4 units to the right. My k would be 2, because I'm shifted 2 units up. So it would be y minus 2 squared. Then we put that over, or write 2 fractions, over the x1 or the longer axis over the a squared. Remember, a refers to the major axis. So if this had been elongated upwards, the a would be underneath the y, not the x. But since it's longer horizontally, the a squared is underneath the x. And our a is from the center to a vertex. So that's, if you'll notice, 4 out to -1 is 5. So this would be a 5 squared, or 25. So this number would be 25. B squared, again, B is the distance from the center to a covertice. And if you notice, that's 1, 2, 3 units. So it'd be a 3 squared, or 9. And that always equals 1, which is really nice. Always equals 1. So again, just to reiterate, this would be x minus 4, because I have a 4 horizontal shift, squared, over 25, because the distance from D to a vertex, the center to a vertex, is 5, and 5 squared is 25, plus y minus 2, because it's a vertical shift of 2, in parentheses squared, over 9, because b is 3, and 3 squared is 9, equals 1. Now again, one last thing to remind you is that a squared is underneath the x only because we're elongated horizontally. If this had been elongated vertically, the a squared would be under the y, because that would be the major axis. Hopefully this will allow you to do the homework today. If you do have any questions, be sure to get on and ask me your questions.